written up here the formulas for our unit tangent vector and our unit normal vector. And these are the same formulas whether we're in 2-space or 3-space. If we have a smooth curve, the unit tangent vector is guaranteed to exist. It's just our derivative normalized. Okay. The unit normal vector is the derivative of the unit tangent vector normalized. So we are taking a derivative a second time, but we are not just taking r prime, because in between taking the derivative here and then taking the derivative here, we normalized. And so it is not the same as r double prime, and in fact the unit normal vector does not necessarily point in the same direction as r double prime. R double prime is not guaranteed to be orthogonal to r prime. T prime is guaranteed to be orthogonal to t, and that's because t had a constant magnitude. It was a unit vector. Now, if we're in 3-space, we can define a third vector. This one won't make any sense in 2-space, but if we're in 3-space, we can define b of t, which is the unit binormal vector. And that's just defined as t of t crossed with n of t. So it's going to be mutually perpendicular to these two vectors. Since these two vectors are not parallel to each other, and neither is 0, their cross product will not be 0. So this will actually be perpendicular to t and n. And you might say, well, with these guys we had to normalize. Do I have to normalize this? The answer is no. It's automatically going to be a unit vector. That's because the magnitude of b, well, it's t cross n. So that's going to be the magnitude of t times the magnitude of n times sine of theta, where theta is the angle between t and n. But that's 1, because t is a unit vector. That's 1, because n is a unit vector. And that's 1, because t and n were perpendicular. So the angle between them is pi over 2, and sine of pi over 2 is 1. So b is already going to be a unit vector. Kind of nice. Now what this does is this gives me a floating frame of reference. Usually our frame of reference is the axes. We've got the origin as our reference point, and then we've got the x, y, and z axis that fix 3 mutually perpendicular directions. Well, the T and B system is just constantly adjusting. So as I move along a curve, my reference point is the point on that curve, and I always have 3 mutually perpendicular vectors, one of which is tangent to the curve, one of which is, well, the other 2 would actually make right angles with the curve, but one of which is we call the unit normal vector, and one of which we call the unit binormal vector. So it's sort of like a floating frame of reference, a floating set of axes that are always adjusting themselves to be in line with the curve. Kind of a neat concept. Now, there are some applications where you're working with the T and B system quite a lot. We're actually just going to see it in this section and then move on. So I'm introducing it as a very neat thing that some of you might see more extensively in another class, but it's not something that we're going to be working with a lot. Within that system, though, if T, N, and B sort of replace I, J, and K, they sort of replace the unit vectors that point in the directions of our axes. We're just rotating our axes and constantly adjusting so that we're doing things in reference to the curve. We can also generalize the coordinate planes. So I could calculate the TN plane. I could calculate the TB plane. And I could calculate the NB plane. Now, each of these planes has another name, and they're given in the text. One of them is the rectifying plane, one of them is the normal plane, and one of them is the osculating plane. I don't remember which is which, and I don't expect you to, because we're just seeing this once and then moving on. Okay? So, if you're asked in the homework to calculate the osculating plane, just flip back in the text and see which of these planes is the osculating plane and then calculate it. if on an exam or a quiz I'm going to ask you for one of them, I will use these names. Okay, so the TN plane at a point would be the plane that T and N would lie in, so they're parallel to that plane. That would mean a normal vector to the TN plane would be B. Whichever vector doesn't occur in the plane is going to be normal to that plane. The two vectors that do occur in the name of the plane are going to actually lie in that plane, at least when they're drawn with their tails at the point on the curve. So let's just practice one of these. So let's let r of t be t squared sine t e to the t. Okay. And let's find an equation for the NB plane when t is equal to 0. Okay, so if I'm finding a plane, I need two things. I need a point and I need a normal vector. Now I have to be careful here because N, capital N, is talking about what's normal to the curve. Here I'm talking about something that's normal to the plane. I'm going to use a lowercase n for that. Okay. All right, well my point will just be r at 0, which in this case would be 0, 0, 1. Okay. Now, what's normal to the NB plane would be t of 0. But if I'm feeling lazy, I know that I can use any vector that's parallel to that. Okay. So if I want to, I could just use r prime of 0. Okay. Because I know the unit tangent vector is just the derivative normalized. But when I'm trying to find an equation for a plane, there's nothing that says my normal vector has to be a unit vector. So similarly, if I were finding the TB plane, I would know that n, the unit normal vector, was going to be normal to the plane. But n is just t prime normalized. I'd probably just find t prime and use that. Okay, so let's find r prime of t. R prime of t is going to be 2t cosine t e to the t. So r prime at 0, which is what I'm going to use as my normal vector n, is going to be 0, 1, 1. Okay. So now I can use point normal form. Now I always sort of like to remind myself of how point normal form works. So we've got the point 0, 0, 1. I'm just going to think of that as being P. I'm going to choose Q to be an arbitrary point, x, y, z, that lies on my plane. But that means that PQ, which would just be x, y, z minus 1, this is now a vector that's connecting 2 points on the plane, so it's parallel to the plane. So what's its relationship to the plane's normal? It's going to be orthogonal to that. So that's what my point normal form is going to have me do. So we will say n dotted with PQ has to equal 0. So that's 0, 1, 1 dotted with x, y, z minus 1 is equal to 0. And so let's see. I want to work out the dot product. That kills off the x's. Y plus z minus 1 equals 0 would be an equation for the, what plane was this? This was the NB plane when lowercase t, my parameter, is equal to 0. Okay. So this is just finding an equation for a plane in point normal form. It's just recognizing that whatever two vectors show up in the name of the plane, the third one that doesn't show up in the name is what's going to be normal to that particular plane.